In the course so far, we have worked hard at doing the general theory of affine varieties and now projective varieties in the last chapters. And now it's time to take a bit of a break from this general theory and just look at a cool class of examples that are also important in the more general theory. And these are the so-called Grassmannians. To motivate them, note that we had projective space Pn, and we started, when we discussed it, by defining it as the set of L inside Kn plus 1, where L is a one-dimensional linear subspace. And we worked on giving this the structure of a variety. So, and this is more generally an example of what is called a moduli space. So this is, we start with some set of geometric objects. So in this case, for example, these one-dimensional linear subspaces of a given vector space. And then we endow this with extra structure, in this case, with the structure of an algebraic variety. And this is what we're also going to do in this chapter. And the kind of mathematical objects that we want to look at is we generalize these one-dimensional subspaces and now look at k-dimensional linear subspaces of a given vector space. And this is already the definition. So if you fix n and then some number k between 0 and n, then you can look at grk, n, the Grassmannian of k-planes in k to the n. And this is, as it said, just the set of L inside Kn, where L is a k-dimensional linear subspace. And of course, as we saw above, the Grassmannian of one-dimensional subspaces in Kn is exactly Pn minus 1. So here note, we had the convention that Pn sits inside, is the linear subspace of Kn plus 1, so that Pn is n-dimensional. But now with the Grassmannians, we don't have such a shift. We just say k and n for things inside Kn. And I do apologize that, somehow both our field is called k and the dimension of the subspace is called small k. I try to use notation that you can distinguish, but when talking, it's hard to distinguish this. Okay. So, so for k equals 1, we already know the Grassmannian, and it has the structure of an algebraic variety. That's fine. Moreover, as a second interpretation of these Grassmannians, note that if you look at the standard projection map from Kn minus 0 to Pn minus 1, then if you have a k-dimensional linear subspace inside Kn, and you intersect it here, and you project, then you get a subset of this Pn minus 1. This subset is exactly the same thing as this P of L, if you see L as a cone inside Kn. And so this is the projectivization of this linear subspace. And going to the projectivization, this reduces the dimension by 1. And so if you start with a k-plane, then you get a k minus 1 dimensional projective linear subspace. And this is basically one-to-one correspondence. So you can also interpret this 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 should be grkn, as the set of k minus 1 dimensional projective linear subspaces inside projective space. So I either see it as k-dimensional spaces in the vector space or as k minus 1 dimensional spaces in this projective space. And our goal here is to give this the structure of a variety. And we're not going to do the thing that we had in the last time by saying, okay, first we give it a Zariski topology, and then we define regular functions, and then we check its variety. But we have now enough stuff lying around that we can instead write down an injective map from this Grassmannian into some big projective space and show that the image of F is closed. And with this, of course, once the image is closed, it is a projective variety. And then we just import this structure and say that the Grassmannian has this projective variety structure. So this is the kind of third such embedding that we have seen. And I want to motivate a bit how you can do this. And this will give kind of a preview and motivation of what we're going to do in the chapter. And the idea is, well, if we want to go to this big projective space, then of course here we have some coordinates, the n+1 coordinates on this projective space, which would give us coordinates here. So if we wanted to have such a map, we would certainly need to have some coordinates on the Grassmannian, which are unique up to scaling. And this outlook then says, well, how did we do this the last time? When we had the projective space of one planes, then what we did to get coordinates is we just chose a generator, right? We had the linear space, and then this had a single generator, not necessarily unique, but the generator is unique up to scaling. And then similarly, well, if we are a Grassmannian, then we are k-plane. So L is a k-plane, so we can choose a basis, V1 up to Vk. And all of these are n-dimensional vectors. And then we can put them inside a matrix, right? We can just have them as the columns of a n cross k matrix M. And then we want to extract some coordinates of this matrix, which are more or less unique, or maybe unique up to scaling. And it's no longer true that the individual entries of this matrix are unique up to scaling, because, for example, you could swap two columns and then this would completely change the coordinates without changing the linear space. What we do note is that this choice of V1 up to Vk is not unique, but it is unique up to column operations, right? We can, changing the basis would correspond to a column operation, which is a right multiplication with a matrix S inside inside this GLKK, so K cross K matrix over the field K. And then how can we extract some invariance under this multiplication action? Well, if you choose some set of k rows of this matrix, then this gives you a k cross k submatrix, right? Because there's k columns here. And then what you can do is you can take the determinant of this submatrix. This gives you one of the maximal minors, pi, of this matrix M. And if you assemble all of these minors, then you get a vector, which we call PL, containing all these determinants, and the set of possible choices of k rows in this matrix of n rows is exactly n choose k. So that's very abstract. So if you, for example, M was this matrix, so in other words, the linear space L you look at is the space spanned by these two vectors here, then you get n choose k, so 3 choose 2, so 3 different maximal minors. Namely, you can choose the first 2 rows, and then the minor is just 1 times 4 minus 3 times 2, so this is minus 2. And similarly, for the first and third, and the second and third, you get a minor. So in this case, this vector here would have these 3 numbers as components. And what is the good thing about these maximal minors? Well, now suppose we act by some matrix S from the right. So you replace M by M times S. This would correspond to choosing a different basis here. What happens to all of these minors? Well, in fact, I mean, right multiplication commutes with choosing some sub rows of the matrix. And so, in other words, the determinant of this new matrix here, if you choose the rows in the set I, is just the same thing as first choosing the rows I and then multiplying. And then we know the determinant is multiplicative like this. This here, this determinant of mi, this is the old coordinate, pi. So what we see is that this pi in the new matrix is just scaled by some scalar determinant of S. In other words, all of these pi are just scaled by the same number. And this means that if you consider this now as a vector inside this projective space, then it is well-defined. So we did get some coordinates which are invariant, which are well-defined up to scaling. And we put this in this big vector. And in particular, we get a map from this Grassmannian to this projective space, sending L to this vector of maximal minors. And this map is what is called the Plücker embedding. And we will check in this section that, or in this chapter, that it's injective with closed image is exactly what we wanted. So this gives the Grassmannian the structure of a projective variety. Now, as I said, somehow this discussion was pretty quick and I didn't give any proofs. The main intention behind this is that to motivate what comes next, because you see the discussion above, this talked about these determinants and submatrices and so on. And this is very hands-on. You can see what's going on, but it's also nice to have a more abstract description of what we're going to do. And this more abstract description will use a concept from linear algebra called alternating tensor products. And so instead of just starting with this section by saying, well, definition alternating tensor products, I wanted to show you this is what is going to come out in the end. So somehow these concrete determinants of submatrices. But in the next videos, we're going to see this abstract linear algebra discussion, and this will help us prove things like that this is an injective map with closed image and so on. So next, buckle up for some linear algebra revision.